My name is Monika Kreitmair, and I work with Alistair Borthwick and Han van den Bremer on the quantification of uncertainty in tidal power assessment. So what I mean by that is I'm trying to understand how uncertainty you have in your input parameters and your input conditions that you use for to model tidal energy. So how those uncertainties impact the power estimates and the average power estimates you get from these models. Today I'm just going to give you a quick run through of the research I'm doing and some of my preliminary findings and what I'm hoping to do next. Okay, I'll start by talking about the motivation behind this research and what hopefully it will be and what the potential benefits would be. I'm going to take you through a simple model by Garrett and Cummins that I'm using at the moment to analyze the effect of friction uncertainty. I will talk about my approach and what I've found, what the preliminary outcomes of this have been, and what I want to do next, basically. So motivation is, if most of you have been here for Stephen's talk, there's some, there's significant uncertainty involved, specifically within the bed friction coefficient, as in there's not much consensus about what exactly it should be, and a lot of the time the numerical models used just use the bed friction coefficient as a calibration parameter until the models kind of give up good results with observations. But so and in general, if you have highly energetic flows such as in the Pentland Firth, which is, as James mentioned, the high currents there can become pretty violent, can give up pretty violent sea states. So it's difficult to accurately specify your input domain, and it's got both spatial and temporal fluctuations. And because of that, your input parameters and your boundary conditions can be ill-defined, and they're a source of some uncertainty. So this then in turn impacts the confidence bound that you can place in your power assessment, and there's a wide range of estimates within the power potential, for example, of the Pentland Firth. So within that, because a lot of the models used are depth average, an important parameter is the bed roughness coefficient. So that's something I'm trying to look at the moment, the effect of uncertainty there on the power assessment. I don't blame you. It's pretty cold in here, yeah. So the picture on the bottom right is an illustration of the impact of spatial distribution of the bed friction coefficient. So here this is in the inner sound of the Pentland Firth, where the tidal array has been optimized, and then they've done a sensitivity analysis on this to see if you spatially vary the bed roughness coefficient, how does that impact the power available? And it can have a pretty significant impact. Right. So, and so one of the outcomes of actually understanding how uncertainty affects your power assessment is that you are able to make better policy and better planning decisions, given that some of this uncertainty is irreducible. Some of this uncertainty will remain inevitably. So my approach at the moment is to look at a very simple piece of analytic work done by Garrett and Cummins in 2005, where they look at a simple one-dimensional channel, and it's connecting two infinite basins, and you have it's tidally driven, and they get this non-dimensional governing equation, and for a linear drag coefficient, where here the drag coefficient characterizes the effect of the turbines, kind of importantly. And so you've got this very simple equation, and you get your power dissipated in terms of this turbine resistance. And so despite its simplicity, it does exhibit this property of having this optimum power point, this optimum dissipation point, where if you're below it, you just don't extract enough energy, so you're performing suboptimally. If you're above it, you resist the flow too much. You offer up too much resistance to the flow, and this is an optimum for the non-dimensionalized case of your friction parameter lambda equaling to 1. So I just wanted to see what happens if I introduce uncertainty into this. So namely, what if I assume that lambda is a random variable with a given average value, its mean, and a standard deviation with which it fluctuates about that mean value. So we do this, and we assume that this has a laser pointer. Yes, we assume that the friction parameter has a probability density function, which describes how its probability is distributed. And then because lambda is a random variable, the power itself will also be a random variable. So what you want to do is you want to get the PDF for the power in order to then determine what the average power is and what the fluctuation on that average power is, given the uncertainty you've just introduced. So by sort of conserving probability, you can just transform it up and across. You do a PDF transformation, and you get your PDF for the power, and you can work out the expected value and the variance in power by calculating the lowest order moments. If you do this if you do this, you can generate a kind of surface like this, where along the x-axis you've got the expected friction, so the mean of the friction that you put in. Along the y-axis you've got your variance, so how much it again fluctuates about that value. And then for each of these, you can work out, by doing the integral, you can work out what the average or the expected power is for each of these things, for each of these x and y points. So, and the green line is so for zero variance. So if you have again your perfectly known average friction, you retrieve the deterministic curve, which is the one we saw earlier, which is good. And then you also see this. So the red line is if you follow the deterministic optimum. So that's for a expected friction value of 1. And then there's also, and you can see that drop off. And as you increase your variance, your fluctuation about your average friction, that drops off. And then you also have this blue line, which tracks the maximum value of the expected power. So those are two interesting features that come out of this. So the first one is you start introducing uncertainty, you will get a reduction in power. So this is kind of inevitable, because you are no longer certain. You can't be certain that you are operating at your optimum value of lambda. So you will be working either side of it, which means you have a lower average power. So this makes sense. However, you also get that the drop off of power along the deterministic optimum. So the one you'd be designing at if you didn't think about uncertainty is lower than it necessarily needs to be. So if you change your design parameters, so if you increase your expected friction, if you increase that, you're actually able to then track a higher average power than you otherwise would with ignoring the effect of uncertainty. Right. So, and that's kind of where I'm at the moment. I'm not sure how long that was, but that's kind of where I'm at the moment. The two main findings I have so far is, okay, you introduce uncertainty into your system. Inevitably, your power will decrease. Secondly, if you want to design more efficiently under the consideration of uncertainty, you want to put in more turbines, or you want to offer up a higher resistance from your turbines. So what I'm working on at the moment is trying to get some kind of the expressions for the average power and the variance in the power in terms of the friction parameter, because that way you get a better feel for what aspect of the uncertainty is it actually leads to this decrease in power and the necessity for more turbines. So although it's mainly down to the shape of the power function. So next is also, so far this lambda has characterized really only the turbine resistance to the flow. But what I really want to do is to look at the uncertainty in the background friction, so the bed roughness coefficient, how that impacts your power estimates. So that's going to be my next step, and to include non-linearities. So because the system is linearized, you get this very nice simple analytic solution, but that's not necessarily very realistic, although it does give some kind of initial results. Ultimately, so in my first year of my PhD, I wrote a finite volume solver, and I want to use that one, which I will ultimately use to perform Monte Carlo simulations to validate this methodology, and to see whether it's actually correct. So that's my work so far. Thank you.
This production is brought to you by the University of Edinburgh.